Assalamualaikum warahmatullahi wabarakatuh. Welcome again to my Reservoir Lab channel. So our today's knowledge sharing will go through overview on short talk, introduce the reservoir quality and fluid sensitivity, specifically rock fluid interaction issue. So in the outline, main areas of fluid sensitivity included fine migration, water sensitivity, acid sensitivity, and pore type itself. So I'll be talking about two particular topics, and these settings aim to provide an overview of reservoir quality and the impact of a different fluid on the properties of the rock. In the context of reservoir quality and fluid sensitivity, fluid sensitivity itself can be categorized into three main areas. First, fine migration. Second, water sensitivity. And the last one is acid sensitivity. Fine migration involves the movement of clay particles like kaolinite, illite, silicate fines, and carbonate fine within the reservoir itself. So understanding this aspect is crucial, especially for assessing the impact of fluid properties on reservoir behavior and any potential issues related to clogging or reactivity. In the context of reservoir quality and fluid sensitivity, fine migration again refer to the movement of fine particles within the rock formation. Kaolinite, illite, and silicate fine, and also sometimes carbonate fines are common type of particles that can contribute to the fines migration issue, potentially affecting the fluid flow of fluid in the reservoir. So the following slide, we're gonna see some side of kaolinite. A kaolinite is a type of clay mineral commonly found in reservoir. When observed up close, it appears similar to a talcum powder pushed into the core surface. This mineral can be identified within the pore system of a core sample and is known for its autogenic growth. When specifically mentioning kaolinite, a type of clay mineral described it's as autogenic kaolinite, meaning it has grown in place within the pore system of the rock. This information suggests that kaolinite is present in the rock samples being discussed and provide insight into its origin and characteristic. So it's ground in place, and the blue part, as we can see in this following picture, I don't know how many of you are familiar with thin section, but in the blue area, when we make a thin section, and then you put a blue stained plastic basically into the pore system. So everything that's blue is the pore system. So again, the growth of kaolinite in the pore system, where under thin section, blue stained plastic is used to represent the pore system. Everything that appears blue in the slide correspond to the pore system. This technique helps to visualize and understand the distribution of kaolinite within the pore system. This is another view of a close-up of kaolinite, a type of clay mineral. The image shown is a scanning electron microscope, SEM photomicrograph, revealing the platelets of kaolinite that are loosely attached to the framework grain within the pore system. This occurrence of kaolinite is quite common in reservoir and can have implication for fluid sensitivity and pore quality. Illite. Illite is a type of clay that is challenging to identify in thin section due to its small size. And to observe it, its magnification of around 500 times with white light is necessary, as higher magnification may result in decrease the clarity. In the pore system, there are numerous specs of Illite, which can be confirmed through the techniques like XRD, X-ray diffraction, and SEM, or scanning electron microscopy analysis. And so this is an SEM photomicrograph of Illite. The Illite particles appears wispy or hairy. So when there is a significant presence of Illite in the formation during injection or production process, such as in the North Sea Jurassic sand, for example, there can be problems with the accumulation of particulate that block the area near the wellbore. The one thing about fine migration that people often forget, that is a fine migrations refer to the movement of fine particles within the reservoir, and these phenomena become a common problem when the wetting pace of the reservoir is mobilized. In water wet situation, if the wetting pace is not being mobilized, fine migration is not an issue because the fine particles are trapped within the content of water. So when wells start producing, an increase in water content known as water cut often occurs. This increase in water cuts lead to decrease in overall production due to the mobilization of fines, which then blocks the pore throat. If the diameter of the fine is 1/3 or larger than pore throat diameter, and there are enough fine present, they will be block the flow. To assess the size of abundance of fine, the small particles in reservoir, we can use a scanning electron microscope. This technique allows us to measure the size of fine and determine their prevalence. Additionally, that we can measure the size of the pore throat, which are small openings in the rock, using either SEM or by conducting capillary pressure experiment. And this kind of measurement provide valuable information for understanding the potential impact of fine migration on the reservoir permeability. In certain reservoirs, such as those found in the Northwest BC or Northwest Alberta, the presence of carbonate fine is quite common. This fine, which are small particle, can potentially cause issues in the reservoir due to their ability to migrate and block pore throat. This information is important for, especially for engineers, to understand the potential impact on permeability and plan appropriate measures to mitigate fines migration. And here we see a significant amount of microcrystalline dolomite. The dolomite present throughout the rock and is encasing the quartz grain and white quartz grain. This information is important for understanding the potential of fine migration and pore throat blockage in the reservoir, which can impact permeability and production. So what happened in reservoirs such as this, where the real acid is injected? The acid primarily interacts with the dolomite fines present in the casings and sandstone. Due to the reservoir's temperatures and pressure, the acid rapidly dissolves this material, but not completely. And this process can lead to the liberation of fines, which may migrate and potentially block pore throat in the near wellbore area, and of course impacting the permeability. And so when real acid is injected into the reservoir containing the dolomite fine, then acid dissolves some of the dolomite, releasing a significant amount of fine. This fine have a potential to migrate, obstruct the pore throat in the vicinity of the well bore, especially when injecting or producing fluid from the particular zone. So the geologists are good with sort of, waving big statement is all you got to find migration problem, but the engineers need to know, well, okay, how much permeability drop are we going to have? I know that we are going to have an issue, but how much of an issue? So the geologists have to identify, you're going to have fines, potentially of fine migration problem. So we will run some tests, and this is an often to get to replicate the reservoir temperature condition. And inside this oven is actually still cylinder with small diameter plugged in it. And so what we do, we're running different fluid using this pump through this small diameter plug at reservoir condition, pressure, and temperature. So we can replicate that what we think will happen down in the reservoir. And so what we do for the fine migration test is we will have very low injection rate and pressure and measure the permeability. So we got this plug, then we have filled this plug with saturated the plug with the formation brine. And so then we start to increase the injection rate. Okay, and what will happen is we will reach, if we have the found migration problem, you reach what we call critical velocity. The critical velocity or critical injection rate. And at that point, you are starting to mobilize the connect water for start, but also the fine. And so with that, we increase the injection rate, and you are starting block a significant amount of the pore throat. And so we can measure that actually. Then you have to scale up this to the field condition. This is laboratory testing, scaling it up in order to get the field condition is always a bit an issue, but that can be done. And then you can get an idea whether I'm going to reduce my permeability by 50% or 90% and etc. And what rate can, if I am doing a waterfall, and what rate should I try to remain below? And is that feasible? Or do I have to go up, or maybe at this rate level, but then I can see I'm going to get whatever 30% drop in the permeability. So now water sensitivity. There are two processes involved with the water sensitivity. Actually, probably the most thought of unknown is swelling, which is a chemical process, and it involves smectite. A smectite usually doesn't occur on its own. It's usually a combination, particular in the, I think, somewhere Western Canada sedimentary basin, for example, it's mixed with Illite. So there are mixed layer clay. That's purely chemical process, what probably most common in those areas. Then people call deflocculation. And dispersion, which is more of a mechanical process, the two result of these two process is pretty much the same. Now you get issue with the clay occupying a large volume, plugging up to the pore space. And anyway, the mechanical process involves detrital autogenic kaolinite and illite. And these clouds are incredibly common in most of a classic reservoir, especially, for example, in Alberta Basin and BC. Now, this is what smectite looks like up closely, and this is SAM. It's common in the upper belly river. I use it this for region to take the sample from this region, and the Viking and also various other formation publicly. But so this is your typical type morphology. What you got to remember is when you are looking at something in a SEM, normal SEM, that you are looking in the collapse state. So any of the volatile of this material has been extracted because the SEM chain chamber has very high vacuum minute. And so any volatiles, any water, any hydrocarbon has degassed, it's been taken out from the state of smectite. But if you introduce water into something like this, what will happen? What will happen is the hydroxyl ions, the OH ion in water that is pressure, then formation water, then will go into any going to occupy the lattice space in the lattice space of smectite, and actually make it expand because OH minus hydroxyl or hydroxyl ions is very large ion, is much larger than surroundings ion. Basically, that's the chemical process. So the flocculation of a dispersion, specifically involving the Illite kaolinite clays, is a process where this clay from larger aggregates due to the presence of OH iron ion. And this cause of the platelets of kaolinite to be pulled apart, reducing the attraction to each other. As a result, the clay lose their cohesive properties and tend to separate, similar to how long distance relationship can lead to the lack of the attraction. And so it's different process. The result is still the same. Is that clay occupies much larger volume and basically plugs up to the near wellbore area. If we introduce material, fresh water or water that is fresher than the formation water, it doesn't have to be fresh, actually just fresher. So using the oven and the steel tube in the pumps, we will get a small diameter plug. Again, we saturate this plug with what we consider to be formation brine salinity. As for examples, up to 60,000 ppm, 60,000 ppm. At this case, this was a study last few years ago in the Cardia. They were looking at water flooding in the North Saskatchewan River water, I believe. This is several years ago. I don't think they have even considered it now, just because the environmental consideration, but this was a while ago and it was, feasible back then. Anyway, so what we do, we got the plug and we throw with the flow, seek for volume, so of up to 60,000 ppm, and then brine through the plug, measure the permeability, and then we step down 30,000, 15,000, up to 8,000, and below between 4,000 salinity. There's a large drop in permeability. So you are pretty low having a permeability here. So this below somewhere between 8,000 salinity, ppm salinity, that we are going to have a significant issue with the formation. There is no smectite in this formation. It's a cardium, but it's full of Illite and kaolinite. And so this stuff, the flocculating that point when you read this below 8,000 ppm salinity, and you have significant issue with their flocculation. So now, we can do the economics and figure out well. We can go in the design of water flood, such as that we can make the basin more saline and inject it, or can we live with reducing the permeability by half and just using fresh water basically. That give you an idea what you can do acid sensitivity. So there are three components. Ferroan carbonate, which is from just basically mean iron bearing chloride, which is ion bearing clay, and bitumen, which we have a lot about here. Some other areas is gas from basin. We had a lot of island in the past. We still have quiet bits in oil now. But what's happened when you flow gas through island and then you leave behind? You take off the volatiles, lighters, and then you leave bitumen. So we got basin that particularly prone to being plugged in many cases with the bitumen. So ferroan carbonate, here what we make a thin section. Generally what we do, we stain it with two things, alizarin red, which stain calcite red. So you can distinguish it from the dolomite. And the other things is a potassium ferrocyanide, which is a nasty things, but it stained an iron blue. So we got the blue stain calcite somewhere here. So it's ferroan carbonate as it's iron bearing carbonate. In this particular case, there's not much the way of pore system shown in this sample. There is a bit of some pore here. Some pore here, very, very small pores. But when this is an SEM photo micrograph, there is calcite cement. This is what it looks like up close. Nice view of some quartz overgrowth on syntax in quartz overgrowth on the trital quartz grain, particular topics. That's just fancy name of the geologists use, I believe. It just mean all in all encasing, so it's surrounding quartz overgrowth. Although the quartz grain, anyway, when you introduce acid into the zone with the iron bearing component, what will happen is the iron will dissolve pretty quickly, the calcite and various other components, and it takes into solution iron as well. But as the pH rise above 3, the capacity for the iron for the acid to hold the iron in solution decrease dramatically. And what's happened is it precipitates out gelatinous ferric hydroxide gel, and again this will plug up your near wellbore area. Standard practice where we know we put acid into the formation, leave it overnight, and come back in the morning, and usually nothing happen because you plug the whole thing up. We learn a lot nowadays, and we do an acid job, then we just get it in out real fast. So you don't leave it down here. This is another interesting slide, I believe, from a petrographic point of view. This is what we call chloride rims. This olive green is sopa, and this is just a word that means an even thickness. Rims have precipitate in this formation, could be bilirubin, acumen, basalt, quartz, cardium is very common in this formation and across the region. You got this multi-state clay precipitates, and it's reflect the original composition of the rock. This kind of the rock, when you just multi-state clay precipitate, you got chloride, then you got kaolinite. So you got two things, two distinct pace of the clay precipitation. This rock, this sandstone actually, generally what we call feldspathic lit arenite. What that means is they got a lot of igneous and metamorphic rock fragment, and they got a lot of feldspar in them. So igneous and metamorphic rock fragment from at very high temperatures, so they are unstable in the subsurface of a few million of years, so they tend to break down, and they are first thing to break down, and what they contain is an iron and magnesium. Hence the name of magnesium and chloride has magnesium and iron on it. So what happened is that pores in that pore system, the pore fluid initially supersaturated concerning iron and magnesium. So the first thing to precipitate out is chloride. So you dissolve all these three grain, a lot of them, then the condition change progress, and the next least stable grain is feldspar, and feldspar is made of alumina and silica. So the pore chemistry is changed to be subsaturated concerning alumina and silica. Okay, so what precipitated is a kaolinite, and this is why you get these two phase in particular formation. This feldspar grain being dissolved, and it's leading to the kaolinite precipitation. And actually I disagree, just because it's very interesting slide. Going back to the acid sensitivity, this is what chloride looks like up close. Think about clay as they have a huge surface area to volume ratio. Then, if you did an XRD of the rock and try to determine the composition percentage, whatever you got in it, it would, for clay, you might get percent or 1 or 2 or 3%. That very significant if the clay are autogenic, which means they are lining the pore system, because there's petroleum engineers, geologists, petrophysicists who are interested in the pore system, just because where's the money is, we hope. And so we introduce acid into the pore system with a lot of autogenic chloride, and then acid will very quickly dissolve a lot of chloride component. And again, it takes the iron into solution, and again, as the pH increase much above 3, it can't hold the iron in solution anymore, so it just spit out gelatinous iron ferric hydroxyl gel, then will plug your near wellbore area. So it doesn't mean if you got all of this case, it doesn't mean that you got an iron bearing material that you can ask and visit. It's just good an idea to know what you are dealing with, so that we can design our production or our operation completion operation appropriately, then our stimulation plan also appropriately. Next is siderite. Siderite is very common in this region, Cardium Viking. This is if you go out to the BC and you go to the dam, it cannot ask is a dam. And probably many of us have been an oil field trip out there, but there is a cardium exposed there, and it looks like there is a ton of rust all over the place of sandstone, and this is siderite that has been oxidized. Siderite is a carbonate, an ion carbonate, and again, acid get indigestion. If the pH rise above the 3, it will precipitate out as a gelatinous compound. Bitumen common throughout in the Western Basin as timid full many log analysis many geologists, many engineers who looks great on log, usually when difficult to produce. But this is bitumen. It's in this particular case, I would call it pure bitumen. People are always asking how you tell the difference between pure bitumen and bitumen. There is no paper that I know that has ever been written to describe, in fact, ever defined pure bitumen or asphaltene. It's a continuum of composition from more asphalt technology stuff with some volatiles in it up to say coke, which is the high end. But this particular case, I think we are looking at pure bitumen because we got this angular sheets-like outline, which suggests this stuff has been baked on or cracked. But the issue of bitumen, particularly asphaltic type, is that acid is water and bitumen is oil. And so if you mix water and iron, what you get is an emulsion. You get a highly viscous emulsion within the near wellbore area. And if you have the asphaltene type of bitumen, pyrite. Years ago, pyrite was thought to be a real issue with acid, would react with acid, but we know that's not a case today. Pyrite is generally present is very small little crystal with class within the particular case. This is chert. There are chert grain, and pyrite generally is not present within the pore system. In this particular case, this is cardium at resinous, which is produced quite a bit of gas in the past. This particular view is not encouraging actually. There's a lot of chloride and this particular pore system right here. But we can see that the pyrite, even the acid did contact the pyrite, which it will not the case because in case with the chart grain, which is generally how we see it, even if did contact with pyrite, is cubic mineral, so it has very small surface area to volume ratio. It would react extremely slow with acid, and it's not like to give you an issue with the ferric hydroxy precipitation. Pore type, as far as we concern, there are two types. There are good one and bad one, effective and non-effective. So this contribute to our productivity, to our reserve calculation, and the non-effective or non-isolated pore do not. So this is a beautiful view of intergranular porosity, which is effective good porosity, good permeability, all the pore volume here pretty well. All of it would contribute or could contribute to your reserve, your productivity, great large pore throat size here, which is the key to connect them to the permeability. Into crystalline or interparticle porosity, this is carbonate equivalent, and effectively we got some nice pore here separated by kind of the fragment. In some cases, we got a lot of micritization, but good porosity, good permeability, and funky carbonate. This is dolomite actually, with some large fog. There's a lot of fog, so they are well connected. They're just not isolated fog. So again, this is contribute to our productivity. And this is micro porosity. This is under thin section photomicrograph and pore throat pore that has been filled with kaolinite. We can see, we can make it out or individual crystal of kaolinite. We can see them all there, but between that kaolinite, there is a lot of blue. Well, the blue is plastic that we use to encapsulate this delicate crystal and to give us an idea of how much porosity was there. If I took slide, was able to push the crystal over the one side, what I would find, if I had one side of the slide just kaolinite and platelets, and the rest of its porosity, half of the volume, and this would be porosity, and the other half would be totally just kaolinite crystal. So that what you are looking at in terms of the volume. I think is 1981 published paper AEPG. There was 3 guys did some studies under SEM study, and they found what they found that the Illite kaolinite approximately half of volume of altigenite, Illite kaolinite in the reservoir encapsulated the porosity. And in similar situation with kaolinite chloride, a smectite but different percentage. Anyway, this is that we can see in the pore, very small pore, an extremely small pore throat. So whatever there is likely not going to contribute to your to our productivity. And in this view, we got 3 types of porosity. A very common intergranular porosity. This is probably where the recoverable hydrocarbon reside. We got the solution porosity in feldspar grain, and this tend to be highly irregular and micro porosity. This is the kaolinite. There's another dissolved feldspar grain. So there's 3 pore type, and they are all that volume. It may be that only the intergranular pore volume contribute to our productivity. So if you do core analysis, if we do core analysis on this, that we are going to get 20% porosity, or we do log analysis on it, then we are going to get a 20% porosity. It's probably only 1/3 or half of that. That's going to contribute to your reserve. So it is important to know that what you are looking at in terms of the pore types. In this feldspar, up close with SEM, we can see this is a highly irregular pore system. So anything in that is unlikely to escape. So it's going to be bound water probably. And here this feldspar being dissolved, and we can see kaolinite precipitating because of that. The solution porosity is not an effective this case, Nordic non-detrital. In this case, we got this rock originally was carbonate, and it was exhumed, it was subaerially exposed to be unconformity, was replaced by chat or by silica. And so this is all now chat brachia largely. So you got this little bivalve or shell critters that have gone to meet the maker. They have been dissolved, and you are left with probably 12, 13, 14% porosity here. But the porosity is not connected, it's isolated. And in addition, you also get bitumen. There's black stuff bitumen, which is plucked off and connecting the pore throat. So pretty good porosity on the log core analysis because we use helium. But in terms of effective, it's not. Now here we have Ledux NSQ, Amphora, one of the well-known fossil name. The dolomite matrix is here. It's tight dolomite matrix. We may have another amphora or city coral. We way over here somewhere. but in between we got this type of matrix. So on the log, we will see porosity or core analysis. You would see this kind of porosity. It will show up, but it was not connected. So looking at the porosity, one of the really important and powerful tool that we can use is mercury injection capillary pressure. We can characterize the pore system, look at the pore throat size distribution, which control permeability. I think one of the published paper at Pittman 1979 SEPM, they were talking about the diagenesis aspect. They wrote about the permeability and examining it using the capillary pressure. It was a really good paper, the seminal paper on the capillary pressure. It's the pore throat zone, not the pore size, producible reserve capillary pressure, obviously, effective versus non-effective porosity, and irreducible water saturation, full package, all things that we can get out of these very powerful techniques. Nowadays, when we do this, we can inject mercury into sample up to 60,000 psi, whereas before we could only get when ED was writing this paper in late 70, only go up about 2,000 psi. Now, so we couldn't get into the micropore system, of course, anyway. Then we will explain later more about it using the Mary. Mary is a Singapore system, McMurray sand, beautiful reservoir. There's permeability in many cases, good porosity, permeability. So what we do with this technique, we take small piece of the rock, could be cube or a plug. Then we start to inject mercury into it. Then this is raw data here, I believe. So here the injection pressure starting 0. Basically, if I repeat one more, so here the injection pressure starting at 0, and this mercury saturation. So it was 100 mercury here. So we are starting ground zero here basically. So what we start to inject mercury, and so we increase the pressure, and what happened as in this particular zone, we got very large pore throat. So after small pressure, we start to inject the mercury into the pore system. So all the pore throat are about the same size. So what happened is you just want a very small pressure band. All the mercury suddenly fills the pore system. So as this close to the horizontal, we got very well sorted reservoir, very equal size pore throat, and right around here. Then, you know, right around 10%, I guess that's your irreducible water saturation in that range. Then we don't get any accurate irreducible water saturation from this method. That would use something else. We got a lot of data over the years. 1,000 of this has been done, 100 of 1,000 probably. Empirically, we can take the pressure data and determine the pore throat size probably. That's in the blue curve here. So the blue curve here. And we can see, I think that's a 10 micron. That's the pore throat radius. So we got 20 micron pore throat diameters. That's huge. Those are really big pore throat. And so they are all about the same size. So that's telling us. So that's the McMurray. So if you take another sample, Belly Reaper, this is, I think, B model pore system. So a little more complicated. The Belly River has got it's got dissolution porosity from feldspar grains. It's going micro porosity. It's got intergranular porosity. So it's got at least 3 different type pore system. But basically major pore system. So here again, we are injecting mercury here. It takes a little more pressure to get the mercury to start to go into the pore system, or the threshold to re-entry pressure pressure is higher than mercury. So this pore throat is a lot smaller from previous sample. That's what telling us. And then this curve, you know, a lot of more inclined. So the pore throat size, there is more range in the pore throat size. That rock isn't as well sorted. The pore throat are different size. So this is intergranular pore system, relatively easy to get mercury into that system. We keep pausing, we get another inflection way up here, then very high pressure, and this represent mercury starting to go into the micro pore system. Sorry. So if I repeat one more time, and this is represent of the mercury starting to go into the micropore system, into the feldspar grain, which much harder to get into. So we got 2 cores. We got the intergranular pore system. We got the micropore system. So taking this data again, empirically, we can got the intergranular pore system with about 1 or 2 micron radius pore throat, and then micropore system is down here, very small pore throat. So it is very good for characterizing the pore system. I pulled this one up just because it's interesting. This is halfway formation, as most geologists would know, is don't have any claim in it. But as people did a lot of work with cap pressure on halfway and found that it had a little bit of micropore system, and thinking, what the heck is that? There is no clay. It's a clean sand, intergranular pore system, and what would lead to that? So final tweet, what we are looking at, I thought it was just instrument error. I don't know what it was, but finally the halfway has to do pore system. It's got integrated pore system, and it's got more micro intercrystalline pores. It's generally got, you know, varying degrees. Fair one, well, could be thrown or dolomite anyway, with the rock as well. And in between this dolomite, micro intercrystalline, like a sheet type porosity. So that represent this micro intercrystalline porosity, which just really show the power of the technique, I guess. So to recap, fluid sensitivity, this fine migration, kaolinite, illite, silicate, carbonate, water sensitivity, swelling the flocculation, and the flocculation is being the primary component in Alberta and BC asset sensitivity. From carbonate chloride and bitumen, pore throat type, effective good ones are not effective. No, so no good important. I mean, not so good. It's important to know that what we are looking at. I think that's all. I hope you find something interested on it, and enjoy my sharing. Assalamualaikum warahmatullahi wabarakatuh.